Good morning, everyone. My name is David Olefeldt, and my presentation here today is on the current and future carbon and greenhouse gas balance of peatlands in boreal Western Canada. And that's a topic which requires you to account for disturbances such as wildfire and permafrost thaw. The presentation today, the results I'm showing, is the work of many. So big thank you to graduate students and collaborators who's been contributing to this. And I acknowledge that all of the research here has been conducted on Treaty 8 and 11 lands in Canada, which is home of First Nations, Métis, and Inuit peoples. So our study region is that of the Mackenzie River Basin, and it is the third largest peatland region in the Northern Hemisphere after the Hudson Bay and the West Siberian lowlands. Most of the peatlands in this region is discontinuous permafrost, so southern permafrost. And as other peatlands, this region has acted as a carbon sink for a long time, but the future is uncertain with accelerating climate warming. And as I mentioned, we have two main disturbances here. It's permafrost thaw and wildfire that needs to be accounted for. So the peatlands in this region have a very distinct morphology, which is governed by the permafrost conditions. So permafrost is only present in the peat plateaus. These are treed bog peatlands with lichens. And then when we have permafrost thaw, we either form thermokarst bogs or fens. Bogs being sort of shielded and not receiving any groundwater, sphagnum-based, and then the fens channel water, so they represent the network, the stream network of these landscapes. And then there's quite some ponds as well in this region. So as I mentioned, peatland permafrost thaw causes the conversion of peat plateaus either to fens or to bogs. And then we have also the wildfire situation. And when a wildfire comes through, it primarily affects the peat plateaus where you have these stunted black spruce that carry the fire. When a fire rolls through the bog or a fen, it's less intense and often doesn't show up much in many months after the fire. So over the last few years, or a bit more than that, me and collaborators such as Oliver Sonnentag's group, we have been trying to understand the carbon and greenhouse gas balance of each of these landforms, which is needed if we want to understand the overall response. And we're using different techniques such as eddy covariance, chamber measurements, or peat core analysis. And the table here shows, it's not comprehensive, but it shows that we are now at the point where we've sort of done all of these approaches to most of these landforms. So I was hoping to get to a full analysis of radiative forcing, but I was a bit optimistic in July submitting the abstract. So instead, we're going to look at three recent developments. So the first, what I'll look at is a comparison of these different methods for the carbon greenhouse gas balance for the bogs. Then we're looking at methane emissions primarily from the fens. And then the third example I have here today is an eddy covariance study of burned peat plateaus. So the first example here is the thermokarst bogs, and we've done the three approaches, peat cores, static soil chambers, and eddy covariance. And the results here, very condensed, shows that there's not an absolute agreement among these methods. The peat core analysis suggests that the transition to a bog leads to a carbon source, whereas direct measurements by chambers and eddy covariance suggest a minor sink or neutral. However, we shouldn't really expect a convergence between methodologies. First, for a few reasons. These studies aren't done at the same sites, and they also look at very different spatial and temporal scale, especially the core analysis looks at the carbon balance over decades to centuries back in time. But if we do look at the overall results, what they do show is that neither of the approaches suggest that we have very major losses of CO2 after thaw. And if we take the average of the three, then it looks like it's going to be relatively neutral, which in turn means that the transition from plateau to bog is unlikely to bring about a huge pulse of CO2, either reduction or increase. So it might not be the main driver of the overall radiative forcing as we're going into the future. So instead, we're going to look at another suspect here, and that is methane emissions. Methane emissions after permafrost thaw have been looked at in other regions, and we've looked at in the bogs quite a bit in this region, but the fens is kind of new. The fens in this region are quite difficult to work in. They're quite wet. The water is being channeled and constrained by the peat plateaus. So I'd say that the fens, or channel fens as they're also sometimes called, are generally wetter than fens south of the permafrost boundary, and they have vegetation that sometimes veers more towards marsh-like vegetation. So this year, Kasia Kempton, a master student in my group, has diligently been measuring methane emissions from one bog and then 3 thermokarst fens, so a poor fen, a rich fen, and an extreme rich fen. And she found very high methane emissions from the poor fen and the rich fen. The rich fen here, with a bit of extrapolation, about 30 grams of methane per square meter a year. That's a large number compared to most wetlands that you find in temperate or boreal regions. Couple of findings here is to emphasize the shoulder season and winter. This is October, just a month ago or so, when we did measurements and still found high emissions. And then another interesting part here is that the region we're in, we can have quite high saltiness to the groundwater. So some of these fens even have lots of sulfate and bringing about sulfate inhibition. So the extreme rich fen here actually did not have very high methane emissions, on par with the bog. So that suggests that methane emissions could be a major driver, but because of methane's shorter lifetime in the atmosphere, you can only account, so to say, more or less for the new areas after thaw. So it's not the whole area of methane emitting bogs and fens that are going to be driving the radiative forcing. So we're going to be looking at that. So our next culprit here, or that we suspect for driving the future radiative forcing balance, would be that of emissions of carbon dioxide from burnt peatlands. And we have to account for both the emissions of carbon dioxide during and in the years after the fire. So Christopher Schulze here is co-supervised between me and Oliver Sonnentag. We opportunistically installed 2 towers in 2019. So this is just a couple of months after a fire came through one of the peatland sites. And we put in another tripod tower there on a site that's only 10 kilometers away that burned in 2007, so 12 years prior. And Christopher, he measured eddy covariance here for 3 years. And these are the annual NEE, cumulative NEE, on the average for those 3 years. So the recently burned site, the 2019 site, had very little productivity during the summer. So we end up with a carbon loss of 120 grams. The site that burned 13 years earlier, the 2007 site, still acted as a source of carbon dioxide, but less so, 15 grams of carbon on average over those 3 years. And that can be compared to an unburned site, Oliver's Scotty Creek Tower that he and Manuel Helbig worked on, which had uptake of 23 grams per year. So summarizing that into a graph here, we have a before fire uptake of carbon. During fire, we estimate, based on methodology here, about 1.8 kilos of carbon being released. And then we have large continuous CO2 emissions for years after, as we're deepening the active layer and we have deeper thawed and often fairly oxic soils on the peat plateaus and very slow vegetation recovery. So it probably takes about 20 years for the NEE to recover to pre-fire conditions or more. So that means that the total combustion and NEE difference is about 3 kilos. And of that, up to 40% is actually in the difference in NEE in the 20 years after the fire. So when you have a fire season like the 2023 here, This year, these effects on the carbon balance of peatlands is not just the immediate carbon loss, but also over decades after the fire. And that's going to be important to account for. Thank you very much.